variables of parameter 1 and a Markov chain. So discrete time Markov chain. And so maybe I'll just recall the definition of our process. So we started from, so here is our set E. Let's say that we started from xi 0, then we defined this time T1, which is tau 0 divided by lambda of xi 0, and we called also this time interval S1. Then the process waits at this time, so the process remains up to time T1 at xi 0. At this time, it jumps to a new point, which is xi 1. So we are following our discrete time Markov chain. And then it remains over xi 1 for a new time interval, which is tau 1 lambda xi 1. And I'm calling this S2, and this time S2, and so on. And we defined xt as the sum. So we are looking at to which interval t belongs. So if t belongs to the interval tn plus 1, so we'll define it as xi n. Okay, so this was our definition. So okay. So maybe let me just remind that Sj, so it's equal to tau j minus 1 lambda xi j minus 1. And this is for j larger or equal than 1. If you wish S0, we can define it as 0. And then Tn will be the sum for j from 1 to n of Sj. And again, maybe let's define T0 to be 0. So this was the definition of our process. It's a very simple process. And what we want to do is to show that xt is a Markov process. So what the theorem I started to prove was that if I call ft the sigma algebra generated by Sxs for s less or equal than t, then what I claim is that the conditional expectation of any function f at time t plus s given ft, that this is equal to the expectation starting from xt of f of xs. Right, so this was the theorem we started to prove. And so let's go back to the proof of this result. So what I said was, well, in order to prove this theorem, what we have to show is that the expectation of the indicator of a function of a set A of x t plus s, we have to show that this is equal to chi A xt f xs. Okay, so this is what we need to prove for all A in ft. Right? Okay. So now what I claim is that it's enough. So this is what I was missing yesterday, is that we will prove this for special sets A. So I'll prove that for A of the form intersection j equal to 1 up to some p, that x sj it's equal to xj. And say that so I claim that it's enough to prove this identity for sets A of this form. So for any p, any sequence S1, Sj, which is increasing between 0 and t, and for any sequence of points xj. Okay? And what I claim is that it's enough to prove that for these type of sets. And why is this enough? Well, so let me call this family, so the family of sets which can be written in this form as D. Okay? So D is all sets which are written in this way. So what I claim is that, well, omega, of course, belongs to D, right? Because, well, you can take p equal to 0. I mean, it's then that the set D, it's closed under intersection. Now, let me call F, or maybe F I used it already, so let me call it G, the class of sets B. So let me call G the class of B's in maybe Ft, for which this identity holds. Okay, so here is the identity star. Then, if I prove that for D, I know that omega belongs to G, because, well, I'm assuming that I proved it for these type of sets. So, in particular, I prove it for omega. Then, the second thing is that if I have an element B in G, then B complement also belongs to G. Right? Because if I take the characteristic of B complement, I get 1 minus B. Okay? It holds for B, and it holds also for 1, because 1 it's omega. Okay? So it holds for complement of B. And finally, if it holds for a family of set Bj, so if I take a set of Bj in G, and these Bj's are disjoint, 2 by 2, then the union of Bj also belongs to G. Just by additivity. Okay, because they are disjoint, the indicator of the union is the sum of the indicators, and you get by additivity that. So this means that G, it's a P class. Well, a P class is a set of family of sets which satisfy these three conditions, and D, it's a lambda class, sorry. And D, it's a P class. And the P lambda theorem tells you that if you have a family G, which is a lambda class and which contains a P class, then G contains the sigma algebra generated by D. But the sigma algebra generated by D, in our definition, by D, this means this corresponds exactly to ft. Okay? All elements in D are in ft. So this class, it's contained in ft, and on the other hand, ft is generated by xs, so ft is also contained in this class, sigma of D, because, well, xs, it's contained in D, and therefore sigma of D contains all xs, which means that it contains the smallest sigma algebra, which makes all xs measurable. So they coincide. I don't need to show that they coincide. I just need to show that it contains ft, but which is also clear, which means that, so this shows that indeed, if I'm able to prove these results for these type of sets, then by this P lambda theorem, you can extend it to all ft. So you know P lambda, the P lambda theorem? Okay. So you can just apply this theorem, and therefore this shows that indeed we need only to prove it for that. Okay? So this is a first simplification. And of course, I can add in this set A, if T is not contained in this, I can add it to it. So I can always assume that the last one, Sj, it's equal to T. Right? Because if it's not, I just rewrite this as the union of all possible values at T, and it's enough to prove now for this intersection, okay? So I can always assume that the last Sj, the largest one, is T. Fine?
Sorry.
Yes.
You are taking the union of Sj plus 1, right? To all the possibilities of when Sj plus 1 is T? I didn't get.
Yeah, I'm saying that I can always assume that the last one, the largest one, it's actually T.
Yeah.
Because if it's not T, I can just add it.
But the way you add it, you consider all the possibilities?
All the possibilities at T.
So the union, right?
The union, exactly. So the union of dot all values, and then I get a sum, and if I prove individually, I get. Yes. This is exactly. Fine. So now, let's start the proof. So let's consider the left-hand side. So the left-hand side, I have A, and as I said, I want to take first, T is fixed, so I want to know what is the interval which contains T. Since Tn converges to infinity, T will be in one of them. So once I do that, now I take, okay. So here comes the observation. Let's assume that once I know that T So let me draw a picture. So once I know that t belongs to the interval tn, tn plus 1, and my set A is this one, is this intersection. So I have here the values of S1, S2, and maybe some of them, well, Sj minus 1, it's here. So this indicator is asking that the process at S1 takes some value x1, at S2, x2, and Sj minus 1, xj minus 1, and t xj, and at x1, x2. Okay, so this is my set A. My set A requires the value at S1 to be x1, and so on. Now, what I claim is that since I know that t belongs to this interval, if you tell me, okay, I don't have red anymore, can you see blue? Well, if you don't see blue on the video, just let me know. So now I claim that if I tell you what are the values of t1 up to tn, which xi1, xi0, up to xin, I can check if I'm at A or not. Okay, because if I know all these values, t1, tn, xi0, xin, so if t1 is here, t2 is here, I know exactly the values in these intervals 0, t1, because I know t1 and I know xi0, so I know the value in this first interval, I know the value in the second interval, until the last interval, which is tn minus 1, tn. And since I know that tn plus 1 is larger than t, well, even if I have values Sj larger than tn, but since they are all smaller than t, and t is smaller than tn plus 1, it's enough to know the value at time tn. But the value at time tn, it's xin. Right? The value at time tn in my construction is xin. So if you tell me xi0, xi1, xin, t1 up to tn, I know exactly if I'm in the set A or not. Which means, this means that I can rewrite the indicator function of A as a function, a certain function, h, of these variables. Okay, I can express this set, the indicator of this set, as a function of these variables.
But the equality holds even if you're not multiplying by the indicator of that requires.
No, I'm here. I'm in this indicator.
Okay.
I'm here. The indicator is set. Now I look at chi A. So let's, if you wish an example, let's say that A contains only one point, and it's xs equal to x. Okay? And I'm interested in the indicator of this function. So, here is t, here is tau n, here is 0. So what I will do is I will write first that S, it's not, let me call that R. So if R is in this set, XR equal to X, it's psi j equal to X. Here I went up to, let's say, n minus 1. So the last one is Tn. And here I will write, well, if S is larger than Tn, then XR is equal to R, sorry, again. R larger than Tn, XR equal to X means that psi n is equal to X. And what I'm claiming is that this function, it's since in this set, this indicator, it's equal to this one. And this one, it's a function of the variables I told you. X0 up to xn, psi n, T0 up to Tn. So I have this indicator, so I can rewrite this function as a function of these values, and this is what I wrote here. So I will replace this indicator function by this function. And I can do that just because I have this indicator. Okay? And here's the example. One, if you have many points, what you have to do is to add all possibilities. Okay, you have possibility for R, then you rewrite the same thing for R2, R3, and so on. Okay? So, and this is what I wrote here, is that I can express H, this indicator, as a function H of psi 0, psi n, T0, Tn. And here is the example. Okay. So this is what I do. I just replace the indicator of A by this function. So I have a sum. Now I have this function H. And keep in mind that it depends on psi 0, psi n, T0, Tn. Okay, but I won't write it. Then I have the indicator of Tn plus 1 of T and F x T plus S. Okay? And now at this point, you know what I will do. I'll just take the conditional expectation with respect to all these variables. And H, which is a function of these variables, will get out. And this piece of the indicator will get out. And then I'll have the other piece. And the other piece is what we studied yesterday. Okay? So this is And here I'm taking the conditional expectation, xi 0, xi n. Okay, tau 0, t0, tn. Okay, but by definition, taking the conditional expectation with respect to 0, tn, or taking it with respect to s0, sn, it's the same thing. And since I know already xi 0 up to xi n, this is the same thing as taking tau 0, tau n minus 1. Okay? So I can replace here tau 0, tau n, t0, tn by tau 0, tau n minus 1. And this is the expression we had yesterday. So yesterday we proved that this conditional expectation now here, okay, I don't remember if we computed this conditional expectation or the one in which I have that t plus s belongs to an interval. Because at this point what I will do, it's in the same way that here we introduce this interval to see whether t, to which interval t belongs, I will do here the same thing. But so we compute it with an extra indicator or just that? With the extra indicator. So let's do this. Let's introduce an extra indicator. So I have now j larger than 0. And so h chi tn less than t. And here the conditional expectation of chi t less than tn plus 1. Now, tn plus j, tn plus j plus 1, t plus s, f x t plus s, condition on xi 0, xi n, tau 0, tau n minus 1. Okay, I just introduced, so since t plus s is larger than t, it has to be in an interval so not really what, so let's say this is larger than 1, and for the other one would be, the first one would be that t plus s is smaller than t n plus 1. Okay, I don't want to introduce in this in this expression Tn. Okay. And this is what we computed. So since t plus s belongs to this interval, I can replace now this object by psi n plus j. And we proved that this conditional expectation was equal to the exponential lambda psi n t minus tn, then the expectation of psi n, so starting from psi n, chi tj plus 1 s f either psi j, let me write it as psi j. Fine? Is this what we obtained? Minus, yeah, maybe here there might be a minus sign. Yeah, okay. So this is what we obtained yesterday. So now, if you sum over j, and with the first term, this, so let's insert this expectation inside here, and now let's sum j, remembering that there is this first term, so that so when you sum over, okay, first I want to replace psi j, since s belongs to the interval tj plus 1. Psi j, it's exactly xs. So let me replace that by xs. And now you see that h and this indicator do not depend on j. This expression also does not depend. So j appears here, and when I'm summing, this becomes 1. So this sum disappears, and what I get is that this sum is equal to the sum in n of the expectation of h chi that tn is less or equal than t, exponential minus lambda psi n t minus tn, and the expectation of psi n fxs. Now, remember that I imposed that at t was one of these points at which we are computing. Yes?
For us to get rid of that indicator, shouldn't the sum start in 0?
Yeah, it starts in 0 because there is this term. Okay, I have to take, when I'm here, I have to take all possible values. So the first one is that t plus s, it's smaller than t1. So this is the j equal to 0 term, if you wish, which will be tn plus 1. And then this is the, So it starts from 0, but this one doesn't. The term 0 is this one. It starts from 0. You're right. We need to include this term. Okay, now I included t. And so in my set A, one of these intersections is that xt is equal to, say, y. Okay, I'm allowed to include t, and let's say that in this intersection appear xt equal to y. Okay, so when I do that, I'm saying that psi n, which is the value of xt, it's equal to y. So in this h, there is the indicator that psi n is equal to y, and therefore I can replace psi n by y here. Okay? When my set A includes the fact that xt is equal to y. And since I know that xt, which is psi n, is equal to y, I can just replace psi n by y. This becomes a number, and therefore I can remove it from the expectation. And what remains is this. I could also replace here psi n by y, but I won't do it. Okay? Now what I claim is, take f equal to 1. So this identity, if I take f equal to 1, is telling me that, so remember, we started from this conditional expectation. Okay. I introduce all the j's. I use the Markov property, and I, at the end, arrived that that conditional expectation without the sum, it's equal to this expression. So if you compare this expression to this one, okay, you realize that what we proved is that this conditional expectation, it's equal to this exponential times this conditional this expectation, starting from psi n. Okay? You look doubtful, so so let's go back here. I have this expression. Now insert the j's. This is what I did here. Use what we proved in yesterday. Sum over j, and you get that. Okay, so if you forget these expressions, what we proved actually was that that conditional expectation is equal to this expression times this exponential. Okay? Now it seems that you agree. which means that if I take f equal to 1, it means that this exponential, it's equal to this conditional probability. And this is what I want to use to say that this is equal to the sum n larger than 0. Then I have the expectation y fxs and the expectation of h chi tn less than t, and here the conditional expectation of the indicator that t is less than tn plus 1, given psi 0 up to psi n, tau 0 up to tau n minus 1. Okay, I'm just applying what we proved to the case in which f is equal to 1. And perfect, because now h and chi are measurable with respect to these sigma field. So I can just put them inside to rewrite that this is equal to expectation starting from y of fxs, the sum of h, the indicator that tn it's less than t, it's less than tn plus 1. And now go backward in my proof. H was the indicator of A. Provided I have this indicator, H coincides with the indicator of A. So I can replace H by the indicator of A. Sum over n to get that this is the probability of A. And this is exactly what we wanted to prove in the special case in which A includes that xt is equal to y, because if I have here that xt is equal to y, I can replace xt by y and move this expectation outside the other one, and this is exactly what we have here. Right? So that completes the proof of the Markov property of this process which I just defined. Okay, and so this is the picture you have to have in mind when we are talking about discrete time Markov chains, right? So you stay an exponential time at a point, then you jump according to a discrete time transition matrix, and you remain in the new point for a new exponential time, which is independent from the past. Questions?
This passage where you remove the conditionless expectation, is it the only time you use that age is a function of this variable?
Yeah. Okay, so we are happy we proved our theorem. Now let me introduce a notation. So for discrete time Markov chain, I had this transition matrix, P, which tells you how you jump from X to Y. So the analogous in continuous time will be to define PTXY to be, well, let's assume that we are starting from X, and we want to compute what is the probability that at time t I am at Y. Fine, but how do you compute this? Remember that I constructed my process from two sets of parameters, a transition matrix and a function lambda. Okay. Now I ask you, well, tell me, provide me a formula for this in terms of P and lambda. And that's quite complicated because if I want to compute that, well, I have to proceed as I have to express xt in terms of xi. To express xt in terms of xi, I have to cut the interval in these sub-intervals t and tn plus 1. So I don't see what I can do besides writing that, well, this is equal to the expectation that tn plus 1 contain t, and xt equal to y means now that psi n is equal to y. Now, so what I know about these times, I know that they are exponential, but the exponential depends on these, the value of the Markov chain. So what I would have to do at this point is to sum over all possible trajectories of the discrete time Markov chain. So this is a sum now over x1, so x1, which is the position at time 1 of the discrete time Markov chain xi. I know that xn is xi n is equal to y, so let me put xn minus 1. And now I have the indicator that xi1 is equal to x1 up to xi n equal to xn, and still the indicator that tn plus 1 contain t. Okay. Well, at this point I can express tn as tau 0 divided by lambda x plus till tau n minus 1 lambda psi n minus 1, and the tn plus 1 the same thing but up to the index n t. Now I could integrate it over tau 0 tau n. I'll get multiple n-dimensional integral, and then sum over all possible paths. Okay? But that's a mess. Okay, I have a complicated formula, and so this is not well. So this shows that it's quite complicated to express in continuous time the probability that your chain visits a point y at time t. So what I want to introduce is another object which is called the generator. And so this will characterize our Markov chain. So one property of PT is that it's a semigroup. in the sense that pt plus s xy, it's equal to the sum of pt xz ps zy, sum in z. Okay, and this follows from the Markov property. So so let's prove this identity. So the left-hand side, you start from x and you want to be at time t plus s at y. So I can rewrite this as the probability starting from x of the probability that at t plus s I'm at y given ft. Okay, but we have seen by the Markov property, so that this is the expectation starting from x of the probability that starting from xt, I am at time s at y. So this is the Markov property, and now I can sum over all possible values of xt. So this is z. I'll get pz xs equal to y, and here the probability that starting from x, xt, it's equal to z. Okay, so if here I insert the indicator that xt is equal to z, and I sum over all z, I will be able to replace xt by z. So this will get out from the expectation, and what I'll get is this. Right? And what is this? Well, this is pt xz times ps zy, which is exactly what I wrote here. So in terms of matrices, what I'm saying is that the matrix pt plus s, it's equal to pt times ps. So this is a semigroup property. Okay? So what I claim is that in our example, so in the construction I have, what I claim is that pt, it's actually differentiable. And I want to compute pt plus h x z minus pt and what I claim is that this converge to pt l x z, where L it's an operator which we will find from this computation, and which is called the generator. So L, so well, I can give you the answer. So L, it's a new matrix, which at xy, it's equal, if x is different from y, it's what I will call Rxy, which is lambda of x, pxy. If y is different from x. So outside of the diagonal, it's positive, can be 0 because pxy can be 0, but it's always non-negative. And at the diagonal, it's equal to minus lambda of x. And in particular, you see that, well, it's always negative. Remember that I assumed the lambda to be strictly positive. And observe that if I sum Lxy, this will be exactly equal to 0 for all x. Okay? Because if I sum for y different from x, remember that I assumed Pxx to be 0 in my construction. I'm not allowing my chain to jump to itself. So if I sum over all y different from x, this is the same thing as summing over all y because I assume Pxx to be 0, and this is 1. So by summing out of the diagonal, I get lambda x, and at the diagonal it's minus lambda x, so it's 0. And what I want to prove is that this is converged too. So here when I write PTL, what I'm doing is the product of these two matrices. I'm doing the product, and I'm computing this product at the point x0. And this is also equal to LPT of xc. So I will prove the first identity and leave it to you to show the second, whose proof is very similar. So I want to prove this, that this limit converges to PTL. Okay. And what I will do is I will use the semigroup property. So by using the semigroup property, I can write this sum as this expression as the sum over all y of p h xy p t yz. So this is the first sum. And now mind that by summing over y here, this phxy, it's equal to 1. Because this is the probability that your process is at y at time h. If I sum over y, I get 1. So I can rewrite this difference in this way. And what I need to compute, so h disappears from this difference. It appears only there. So what I need to compute is 1 over h ph xy. What is this limit? Here, I can assume that y is different from x, because if y is equal to x, this is 0. So I'm computing this limit for y different from x. So this is 1 over h, the probability that starting from x, at time h, you are at y. So again, there is nothing I can do but to repeat my computation over there and to cut my interval in these subintervals tn, tn plus 1. Okay, but I'll do the following. Either T1, it's larger than h. So maybe the first jump happened after h. Okay, this is, okay, maybe. Then, well, the second possibility is that the first jump happened before h, but the second jump up after h. And finally, that the second jump happened before h. Okay? So what I claim is that the last term converges to 0. Okay, why is that so? Because the second jump is the sum of the time of the second jump. It's the sum of this exponential, which is t0 lambda x. This is s1, the time of the first jump. And then I have t1 divided by lambda of xi1. And what I'm asking is this to be smaller than h. Okay? What I know is that tau 0 and tau 1 are exponential 1 random variables. So this is certainly larger than tau 0. Well, I want this to be larger, so I'll take the minimum of lambdas, or the maximum. So let me call lambda star, or lambda max. The maximum of lambda z. So there are finite number. So this max, it's finite. Okay. This means that if this sum is smaller than h, it means that this sum is smaller than h. But now I have, so these are fixed numbers. So this is the same thing as saying that tau 0 plus tau 1, it's less or equal than lambda max times h. So it's the probability that the sum of two exponential mean one random variable is bounded by a constant times h. And this you can compute. And what I claim is that if you take tau 0 plus tau 1 bounded by a constant times h, this is of order, or it's bounded by another constant times h squared. Okay, essentially you're integrating over a region which is a triangular region of size h. So that gives you h squared. Okay, so this is a simple computation. And since it's bounded by h squared, this means that this probability, it's bounded by this one, but this one it's bounded by that one, which is bounded by h squared. I'm dividing by h, taking the limit in h, so this goes to 0. Okay? So the only thing, okay, this one it's also 0. This one is 0 because here I'm starting from x. Why it's different from x? So if the first jump happened after h, my value at h, it's x and not y. Okay? So this is 0, so the only important one is this one. So let's compute that. Okay. So the way I will compute, I will use the Markov property to say that this is equal to the expectation. I will take the conditional expectation with respect to fh. So xh equal to y it's measurable with respect to fh. T1 less or equal than h, it's also measurable with respect to fh. And what remains, it's the probability that T2 it's larger than h given fh. So let's compute this probability. T2, it's S2, which is tau 1. So here, T1 less than h, xh it's equal to y. So this is lambda y. Okay. Here I'm at time h, I'm at y. Or maybe let me write this. Okay, I don't want to. Okay, so to be absolutely. So what I'll have to do here is to repeat what we did before. Right? I have that. Instead of taking the conditional expectation as I wanted h to justify all my steps, I will have to, again, take the conditional expectation with respect to psi 0 and tau 0. So okay, do you accept this argument? I'm taking the conditional expectation with respect to so let's see if you accept this argument. So I'm taking the conditional expectation with respect to tau h. I'm writing this is T2, it's S2 plus T1. So actually this is S2 and by the Markov property, this will be the probability that I'm starting from xh at time 0 and this is the probability that an exponential random variable it's larger than h minus t1. So t1 it's a fixed value. It's the value given by here because since t1 is smaller than h, its value at fh it's known. So it's fh measurable in this set. So t1 is just the value given. And now I'm computing the probability that I have an exponential divided by the value. Okay, that S1. So with starting point at xh, it's larger than this value. So what I'm saying is that this is equal So S1, it's an exponential with parameter lambda of xh, and this value is nothing, it's minus lambda xh h minus t1. So maybe I'm going too fast here, because in order to prove it, derive exactly this equality, what I will have to do is argue again that here I'm conditioning on xi0, xi1, just as we did in the proof of the Markov property. But remember, in the proof of the Markov property, at the end, what we got, it's exactly like that when f is equal to 1. So in order to avoid these computations, try to prove this identity, so that this, so what I'm claiming is that this, can I erase here? That the Markov property we proved, so if we repeat the arguments, we show that this expression, it's equal to 1 divided by h, the expectation that xy it's equal, xh it's equal to y, that t1 it's less than h, and we get this exponential. And we are starting from x. Okay, so try to prove this identity, and if you're not able, we can discuss that on Tuesday. But now, well, xh it's equal to y, so I can replace this by y. Now everything is in terms of t1. So I can just, t1, remember, it's tau 0 divided by lambda of xi 0, which is x, because we are starting from x. So we get xi h, it's equal, xh, it's equal to y. And I can integrate it over t1. So this is, I'm integrating it over up to h. I have exponential minus lambda y h minus s. t1, it's an exponential of parameter lambda x. So it's lambda x exponential minus lambda x s ds. So here I'm integrating over the variable t1, which is an exponential of parameter lambda x. So here is its distribution. The indicator appears here, and here we have a function. And xh it's equal to y, so since t1 is less than h, xh equal to ty means that xi1 it's equal to y. So I can replace xh by xi1, and so this now everything here does not depend anymore on xi1, so I can just write so that I jumped from x to y. And now I have 1 over h multiplying this integral, and I'm taking h to 0. So you see when s is between 0 and h, So this expression will tend to 1. The same thing for that one is between h and 0, so h minus s between 0 and h. So this will tend to 1. I have here factor h due to this integral, but it's divided by h, so that will give me a contribution 1, and this is converging to lambda x. Okay, so this will converge to lambda x times pxy. And this is exactly what I claimed. Okay, so that this is converging to xy, so that this expression phxy divided by h, it's converging to rxy. And what I get is that, so this expression, it's a finite sum, so it converges to the sum in y of what I call rxy, pt yz minus pt xz. Okay, and so as I said here, I can take y different from x, but I can rewrite this as, so sum from y different from x of r xy pt yz minus sum from y different from x or xy pt xz. So this is what I defined as LXY. So for x, y different from x, y different from x, rxy, it's lambda x pxy, and this is the definition of LXY. Okay, so this guy, it's LXY. While this one, you see that I'm summing over all y different from x. So let's see what this sum is. So the second term, it's minus a sum for y different from x, rxy, but rxy, it's lambda x, pxy, and then I have ptxz. So y appears only here. When I'm summing over all y, I get 1, because I'm assuming that pxx is 0. Okay? So this is minus lambda x ptxz. And mind that if y is equal to x, lxx, it's minus lambda x. So this term here, it's lxx ptxz. So now I have a sum for y different from x of lxy ptyz plus lxx ptxz. So this is exactly the product of L with pt at xz. Okay, so questions about this proof, about the conditional expectation, or this last piece of
Yes, can you explain better why it converges
to 1? Okay. So what I'm saying is that you have here a function which depends on s, and which is continuous, and 1 at 0. Okay, so this function is essentially 1 because h is small. The same thing for that one. So this is essentially 1, this is 1, it is constant, and then
Would you need the dominated convergence or no? To prove this formula?
no, just need the continuity of these functions and the fact that they are 1 at 1. Any other question? Okay, so we proved, okay, I proved this. I'll leave it to you, that one. The way in which you prove this one is just, instead of writing pt plus h as ph pt, you just do the opposite, pt ph, and you get the other one. Okay. So I still have time, so I can, okay, so what did we do? We proved the following. So let me write it properly. I define PT, which is these matrices. These matrices form a semigroup. And then I introduce another matrix, L, which I call the generator. And what I prove is that if you take the derivative of PT, this is equal to PT L, which is also equal to LPT. These are matrices, operators. Right? So by looking at that, what you want to say is that PT is actually equal to the exponential t times L. So what's the exponential of an operator? Well, you can define it, say, by the sum of taking TL to the power k, k factorial. So let me define the exponential TL by this expression, and then I have an identification of PT as the sum, as the exponential TL. And this is well defined, because L is a finite matrix, so that will increase the coefficients of L will increase not fast enough to beat the K, so this is well defined. So what I want to say is the following. So you take your matrix L, and I want a bound on the Lij. Infinity in terms of Ij, max in Ij. Okay? So, or to the power k, because this is what's appearing here. Okay? But, so how do I get a bound of this? Let's say that I want a bound for L2. So this is the matrix L times L. So in order to bound this, let's say that so I want to estimate this. So what I claim is that if you take your matrix L, and let me call M the matrix, which is all entries are constant, equal to the maximum of L. And let me call the maximum of L small l. So M is the maximum in I and J of Lij. Okay? So it's clear that this L2, it's bounded by the M2. Okay? And the M2, what you're doing, this is bounded by M squared times the number of lines. So let me call P the number of lines. Okay? And by this argument, you'll get that if you take Lk, well, if I iterate this argument, In the next one, I'm multiplying that by m again. So I'm getting that, let's say, 3 will be bounded by p squared m cubed. Okay, because I'm multiplying this m squared, whose entries are bounded by p m squared, by this matrix M. So I'll get Pm square M cube, but I'm summing P terms, so I get a P. So P square M, and by induction, so that you get that Lk will be bounded by K minus 1 Mk, and therefore this divided by K factorial converge, so this is well defined. So this means that I have a one-to-one correspondence between PT, the semigroup, and the generator. Okay? If you give me a semigroup, I can define the generator by taking the derivative of the semigroup and computing it at time t equal to 0. Because at time t equal to 0, you see that P0 is just the identity. Okay, Pt is the probability that at time t you are at y starting from x. If you send this t to 0, well, you have no time to jump, so that will converge to the identity. Okay, so in particular, if I take the derivative of Pt and I compute it at t equal to 0, I get the generator. So if you give me a semigroup, I get the generator. And if you give me a generator, which means a function in which all the entries are positive outside of the diagonal, they are negative at the diagonal, and the sum is equal to 0 at each line, I can get Pt by this formula and can show that Pt, well, from this equation, it's clearly a semigroup, but it's also conservative in the sense that Pt, if I compute Pt at 1, this is 0. So let me state carefully what I want to say. Let's see what are the properties of Pt that we have. And before I do that, let me interpret these PTs as operators. So I have PT, which I defined. Now give me a function, f, and I will present by PTF a new function. One, yes, sorry. 1, L at 1 is 0. Yes. But let me summarize all what I said carefully. So first, I want to say that if you take, I want to understand Pt as an operator. So if you give me a function, I define a new function. So f, it's a function from E to R. I define a new function which at x takes the value y, ptxy, fy, which I can understand as the product of the matrix P with Pt with the function f. Okay, so this defines a function. So these are operators. So now what do we know about these Pt? First, that it's a semigroup. In the sense, we proved that Pt plus S is equal to Pt ps. Then, as I said, P0, it's the identity. Do you agree with that? Because, well, if I send T, you have no time to jump, so P0, it's the identity. And then, well, we proved that Pt is differentiable, so something weaker is that If I take PTF and I send t to infinity to 0, I get f. Okay? So these are called, okay, now we are working in a finite state space, very simple, but we could be working in a Banach space. You have a norm, you are in a Banach space, you have an operator in this Banach space, which satisfy these three properties, and here I would require that in the norm of the Banach space. I would say that an operator which satisfies these three properties is a uniformly continuous semigroup. Okay, in our context of finite state space, of course, if it converges pointwise, it converges uniformly. So we proved all this. We have these three properties, but we have more. We have that PT is positive. So if I take a positive function, PT sends positive functions to positive functions. In the sense that if f is positive, then PTF is positive. That's clear. And it's conservative because if I apply PT to 1, I get 1. Just the fact that the sum of PT xy is equal to 1. This is equivalent because I can take f, the function f, to be the function which is equal to 1 at y. You fix a point y, and you say that f is 1 at y and 0 everywhere else. When you compute PTF, you get PTXY. Okay? And so this is saying that PTXY is converging to 1 if y is equal to x, 0 otherwise. So this is saying, this is equivalent to say that PTXY is right continuous at t equal to 0. So in our context, saying that PTF converges to f for all f, it's equivalent to say that PT is right continuous at 0. Fine. Now suppose I have this. I can define L as this equation taking the derivative. In other way, I would define L as the limit as h tends to 0 of PHF minus f divided by h. Right? You get from this is what we were doing, okay, when we proved that you have these derivatives. Take t equal to 0. This is saying that pH minus the identity is converging to L. pH minus the identity divided by h, it's converging to L. Okay? So here, what we proved is that for all functions f, this limit exists. Okay? When you are in an abstract space, so in a Banach space, this limit, so you start from your semigroup, which you constructed. Now you want to prove that you want to define this operator L. Well, it turns out that L will not be defined for all functions f. So this limit will not exist for all functions f, but it will exist only for a class of functions that you will call the domain of definition of this operator. And this is part of the Hill-Yoshida theorem, okay? That how to construct a generator starting from the semigroup, which in our situation, it's very simple. We just did it. If you give me a semigroup in a finite state space, I can take its derivative, and I can define the operator, which gives me the derivative of the semigroup at 0. And this is what's called the generator. And if you give me lambda and p, I know exactly what is the generator, right? The generator is a new matrix which is expressed only in terms of these lambdas and p's. So now, what are the properties of this generator? Well, L1, it's equal to 0, because if PT1, it's 1. And we have seen from this computation that, so what means that L1 is equal to 1? This means that the sum of the lines are 0. Okay. And we have seen furthermore that actually L, it's a matrix in which the diagonals are negative and the off-diagonal terms are positive. Okay, and they sum up. And now if you give me such a matrix, so a matrix in which you have these off-diagonal terms positive and the diagonal terms negative, and which satisfy L1 equal to 0, I can define PT as the exponential TL. And I will get these properties. So what do I mean by this exponential TL is exactly the sum. The sum is well defined in finite space. Okay. And let's see these properties. Well, you have the semigroup property. This is a consequence of the exponentials. P0, if you take t equal to 0, the exponential at 0 is just the identity. Okay, if you look back to our definition, you have this sum. When k equal to 0, this is the identity for k equal to 0, right? Power 0 of a matrix. So indeed, and PTF will converge to F because you have more than that, right? If you go to this formula, you'll see that all terms which are for k larger than 1 will converge to 0 and will remain the term when I send t to 0. So indeed, I have PTF converging to F. Actually, I have more than that. We can show that PTF minus F divided by T, so will converge to L of F. So we have more than continuity, we have differentiability. So, and this is another way of saying that L, it's equal to the derivative of Pt at time t equal to 0. And this is exactly what we're computing here. And the fact that it's conservative comes from the fact that L1 is 0. Okay, and the fact that it's positive for positive functions is just an exponential. Okay? So, a last comment. So please prove that the second piece, which I didn't prove, just to check that you understood. Okay, I didn't say also, now I'm following the appendix of my book with Kipnis. So the first appendix. So I'm following here the appendix 1 of my book with Kipnis. And I want to say one more thing about these generators is that, so assume that I give you L, which is a generator. So meaning that I'm telling you what is the matrix LXY. And I want to recover from LXY the values of P and lambda. Okay? Lambda, it's very easy because I know that LXX, it's equal to minus lambda x. Okay? So if I tell you what is L, you can recover lambda. And once you have lambda, you can get LXY, because you can get P, because LXY it's lambda x or x pxy. And therefore you get P by dividing LXY by lambda x. Okay, so if I give you L, you can recover the parameters lambda and the jump probabilities P from these equations. Okay? But if I tell you only LXY for x different from y, you can still recover everything because you can sum over y, LXY, remember that y different from x. So if I tell you y from, so this is exactly lambda x, right? Because you know that the sum of the line has to be 0, and that on the diagonal it's minus lambda x. So the sum for y different from x of LXY should be lambda of x. So from this equation you recover lambda, and from once you have lambda, you recover P. So if I give you the generator, you can tell me what lambda is, what P is, and then you know exactly how is your Markov chain. Right? If you are at x, you wait an exponential time of parameter lambda of x, then you jump to y with transition matrix Pxy. So all the information is contained in the generator. And this will play the role of P in the discrete time Markov chain. If I give you P, you know exactly what your Markov chain is doing. Now if I tell you what is the generator, you know exactly what your Markov chain is doing. Okay? So the way in which you describe a Markov chain, you characterize a Markov chain, is giving its generator. Here, in finite state space, the generator is just a matrix. It's defined everywhere. In more general spaces, you may have two. So typically, let's say that the generators will be given by differential operators, say the Laplacian. But you can have two completely different processes with the same differential operator. What will allow you to distinguish, to know exactly what process you are referring to, is the domain. So the domain is extremely important. Well, this is just an observation for you to keep in your mind, so that it's not only enough to tell you what is the operator, you also have to tell what is the domain. Okay, so with this we conclude this lecture. If you have no question, and we continue on Tuesday.